Yes, we can hear
Yeah.
you.
Is my screen visible, ma'am?
Yes.
Yes. Okay.
Okay.
Thank you. Yeah. Uh, Good morning and warm greetings of the day to everyone, including organizers, committee member, and to all attendees. I am Sharanjeet Singh, pursuing my PhD under the supervision of Dr. Dilip Kumar at UGC DACSR Indore. I am delighted to present my research work on the enhanced thermal stability of magnetic anisotropy in obliquely deposited magnetic films on the nanopatterned substrate. So let's begin by outlining the structure of today's presentation. We will begin with an introduction to magnetic anisotropy and its application. However, there are some challenges in creating the magnetic anisotropy in polycrystalline thin films. So we will discuss how to achieve it by exploring two methods. One is ion beam induced nanopatterning and the other is by oblique angle deposition method. Then finally, I will conclude my presentation by discussing some of the important results highlighting the enhanced magnetic anisotropy in the polycrystalline films. So let us first discuss why thin film nanostructures are important. Because these two-dimensional nanostructures can give peculiar magnetic properties, which often has no counterpart in the bulk material. And in literature, people have discussed so many exciting phenomena in this area. And these two-dimensional nanostructures have immense possibility to tailor their properties to achieve the desired functionality. The magnetic anisotropy is one of the most important property of the magnetic material. It refers to the directional dependence of the magnetic properties. If the preferential alignment of the spin is normal to the film plane, then the film exhibits perpendicular magnetic anisotropy, and it has application in spin walls and magnetic tunnel junctions. Similarly, we can understand the in-plane magnetic anisotropy by the preferential alignment of the spins in the film plane. It has application in high-frequency devices and magnetic sensor, etc. The overall behavior of magnetic anisotropy can be understood as the result of four key interactions that are exchange interaction, dipolar interaction, spin orbit interaction, and Zeeman energy. These interactions collectively determine the overall magnetic behavior of a material. And in thin films, the main source of magnetic anisotropy is magnetocrystalline anisotropy, which arises due to the spin orbit coupling. But this is due to the periodic lattice arrangement, which is often realized in epitaxial or single crystalline thin films. So what will happen to the magnetic anisotropy in polycrystalline or amorphous thin films? Here is the Mock loop of the polycrystalline cobalt film taken at two different azimuthal angles. And as we can see, there is the magnetic anisotropy is clearly missing. This is due to the lack of long range ordering of magnetic moments. Due to that, the domains are randomly oriented and practically cancel out the overall magnetic anisotropy. So here lies the real challenge, that how can we create the magnetic anisotropy in polycrystalline films? So here we can utilize the magnetic dipole interaction by creating the shape anisotropy, which can be obtained through nanopatterning or columnar growth. So let us discuss some practical method to induce magnetic anisotropy in polycrystalline films, which are magnetic field annealing, ion irradiation, substrate induced anisotropy, stress strain engineering, and oblique angle deposition. I will discuss substrate induced anisotropy and oblique angle deposition in detail. In oblique angle deposition, the origin of magnetic anisotropy is shape anisotropy. In this method, the material is deposited at some angle with respect to the surface normal. It works on the principle of shadowing effect. The already deposited add atoms causes some shadowing to the upcoming add atoms. So the deposition takes place on the primarily exposed surfaces, which leads to the formation of inclined columns. And these inclined columns can create shape anisotropy in the film, which induces the magnetic anisotropy. We can further enhance the effect of shadowing by using the patterned substrate. By utilizing our in-house developed chamber capable of in situ measurements, we have deposited cobalt film at an oblique angle of 65 degrees on a rippled substrate. For magnetic characterization, we have used Moog technique, and for structural and as well as morphological characterization, we have used XRR, AFM, GSEX, and GVEX measurement at Petra beam lines. At first, we have patterned our glass substrate by using an ion beam of energy 700 electron volt oriented at 65 degree with respect to surface normal. Here is the AFM image taken after patterning, and we can see that the ripples are formed quite periodically. From GSEX measurement of the pristine substrate, the wavelength is found to be 68 nanometer, and the ripple average height is nearby 4 nanometer. And on this rippled substrate, we have deposited deposited the cobalt film at an oblique angle of 65 degree with respect to the surface normal, and the plane of projection or deposition projection is kept perpendicular to the ripple length. The AFM image taken after the deposition confirms the conformal growth of the film, and by fitting the XRR data, the film thickness found to be 35 nanometer. So for magnetic rectification, we have used the MOC in the longitudinal geometry to find the in-plane magnetic anisotropy. The sample has been rotated at various angles with respect to the magnetic field direction, and the MOC loop has been taken at different azimuthal angles. The direction of magnetic field along the ripple length is taken as 0 degree. Here we can see the MOC loop obtained from the pristine sample, which show the magnetization behavior along and perpendicular to the ripple direction, and we have successfully induced the magnetic anisotropy in the polycrystalline cobalt film. The magnetic easy axis lies along the ripple length, which is the long axis here. But the more interesting property emerged out with thermal annealing, we have observed an enhancement in the magnetic anisotropy with an increase in the temperature up to 200 degrees Celsius, which is quite interesting because in obliquely deposited films, there is always a decrease in anisotropy due to the diffusion of columns. So to know more what is happening here, we have done the G-sex and G-vex measurement at Petra beamlines. Here is the G-sex image of the pristine sample, that is in which the X-ray was kept along the ripple length. The vertically aligned periodic lines marks the presence of the ripples, and the asymmetric distribution of the intensity in the left side of the scattering rod shows the presence of tilted columns. When we have taken the line integration along the ripple length and the perpendicular to the ripple length, we obtained these curves. The origin of the satellite peak is the presence of the periodic ripples with an wavelength of 84 nanometer. And this asymmetric broad peak is appeared due to the presence of tilted columns with an intercolumn separation of 84 nanometer. We have done in situ G-sex measurement at different temperatures, and by comparing the curves obtained from the horizontal integration, we have seen that with increase in temperature, the asymmetric broad peak shift toward the lower Q values, which shows that there is diffusion of column. And at 250 degrees Celsius, we can see that the hump is now disappeared, which showed that the columns are completely diffused at 250 degrees Celsius. Also, the satellite peak feature is damping with increase in temperature, and at 350 degrees Celsius, almost ripples are almost diffused, which leads to the isotropic nature of the film, and thus the overall magnetic anisotropy is gone at 350 degrees Celsius. So by G-vex analysis, we observed that the film exhibits in the polycrystalline nature, that is HCP phase here, and there was no texturing found in this film. So we have grown our film on the amorphous substrate, that is glass substrate. So there was no stress or preference for growth, and by G-vex analysis, we confirmed the polycrystalline nature of the film, and there was no texturing. So the magnetocrystalline anisotropy is clearly missing. So the main source of magnetic anisotropy here is the shape anisotropy due to the ripples and columns. The competition between ripples and columns to align the easy axis along their lengths is the possible origin of the enhanced magnetic anisotropy with thermal annealing. Actually, ripples try to align the easy axis along their length, and nanocolumns try to align the easy axis along the projection of columns, and thus creating a competition between them. But with thermal annealing, we have seen that the column tends to diffuse, which reduces the magnetic anisotropy component due to the columns, and the highly porous columns present in between the ripples connects, and thus increases the effective shadowing, and which leads to the increase in the magnetic anisotropy component due to ripples. Thus, it improves the magnetic anisotropy of the material up to 200 degrees Celsius, and with further increase in temperature, the column and ripple almost diffuses, and thus reduce the overall magnetic anisotropy. So the overall conclusion of this work is that we have successfully induced the magnetic anisotropy in polycrystalline thin films, and we have successfully enhanced the thermal stability of magnetic anisotropy and established its possible origin. And by using these methods, the uniaxial magnetic anisotropy can be generalized in any magnetic thin films for the possible applications. And finally, I would like to acknowledge the organizers for giving me this opportunity to present my work in this exciting scientific platform. And with this, I would like to thank you all, and suggestions and questions are welcome.
Okay, thank you so much. Yes. Okay. We have a question here. Yes, please.
Hello, sir.
Yes, ma'am.
Thank you for the nice talk. Actually, I want
Thank
to
you.
ask, like, what cobalt thickness have you taken?
What, ma'am?
Cobalt thickness. How much you have taken?
35 nanometer. And we have
35
deposited, yeah, it was found to be 35 nanometer with XRR fitting. We deposited around 50 nanometer in calibration with the quartz crystal, but as it is oblique angle deposition, so the effective thickness was 35 nanometer.
And in the conclusion section, you have shown that there was less dipolar energy in comparison to magnetic anisotropy.
Less dipolar
So-
energy. Yes.
Yeah. So how you get to that conclusion? Like in this system, there is a dipolar energy is less dominant.
No, less dipolar energy along the ripple wave vector was less dominant, and along the length, along the ripple wave vector was more dominant, but along the ripple length, which was the long axis, at that point, the magnetic dipole interaction was less dominant, and due to that, the easy axis lies along that ripple length. So from the easy axis calculation, like the easy axis is lying along the ripple length, we have concluded that the magnetic dipolar interaction along the length, along the ripple length, is less dominant as compared to the columnar direction.
So is there any is there that kind of a study like which shares like easy axis where lies the dipolar energy minimized?
Ma'am, there are many studies on this. One is by D. Verbano, in which they have grown the FEPT nanowires on this rippled rippled surfaces of Al2O3, and they have shown this by using some equation. And I'm also trying to include some equation in my work. I am still working on this paper, on this manuscript, but there are some proof for this.
Thank you.
Yeah, thank you.
Okay, thank you so much for the report. And because we have to keep up on the schedule, can we move on to the next speaker? Thank you for your time.
Thank you. Thank you.
Yes.